Hi, I'm Tariq Khan from Deakin University. I'm going to present my paper of title, T-Net, a resource-constrained tiny convolutional neural network for medical image segmentation. In medical image segmentation, the objective is to segment the features as close to the ground truth. But by doing that, we face a lot of challenges, and most of them are like structural boundary ambiguities, like heterogeneous texture, segmented area uncertainties, large contrast variation, and large image size. Among them, large image size in medical imaging is the most significant one. Why? Because we need, in most of the times, we have large image sizes in medical imaging just to accommodate the features so that they can help in the diagnosis and eventual treatment. So training and testing can be computationally expensive for those large images, and we need to downsample before training is usually required, which is particularly undesirable in medical imaging. So in order to address this problem, so we to keep the others accuracy and other stuff consistent with the state of the art, we proposed a T-Net, which aims at preserving the boundary information and details by using the least possible number of pooling layers. This is since these often reduce the dimension of the feature map and can also cause the loss of spatial information. Further, we have also employed skip connections so as to keep the complexity low, and we have used a small number of convolutional layers. We have also reduced the overall number of convolutional filters within each layers. Why? Because the convolution filters, we have found that like most of the medical image segmentations, we have given only one feature, and the shape variation, if we have calculated, it's not that much. So by using the standard formation, we encounter like feature overlap problems, which not only causes a lot of like a resource eating, but also it also affect the overall performance of the networks. So we have addressed that this problem particularly in this paper. And finally, but not the least, we have used group convolution, and on top of that, we to resolve the imbalance problem, which in most of these image segmentation of medical images do have. So we used a dice loss pixel classification. So with dice loss pixel classification, we use this standard one. So we used several medical image data sets to check the efficacy of our proposed scheme. So first, the filters effects we have found, like if you see, you can see that in standard settings, 64, 128, 256, which is the unit standard setting, it's consuming or eating a lot of parameters, but is giving not that good results. But if we see the optimized one, T-Net, so it's almost far less consuming parameters, but it's in terms of other performance, it's doing quite good. So to check its stability, we did the initial rates, so it shows it's quite consistent, not changing much. And when we compared with state of the arts, we have found like it still gives comparable results on this stair, drive, and other ones. But in terms of parameters, it's far less than the state of the art methods. We also checked this one on HRF dataset because its image size is quite large, like 3K image. So we found like we don't need to downsample that 3K image to train this on our network, which is because of having this small number of parameters. So when we compared with this state of the art performance with state of the art lightweight networks, so we can see our network has outperformed those state of the art like M2U-Net, ERF, or MobileNet v3. So which is and also in terms of parameters, it's consuming far less parameters than this state of the art. So in conclusion, so our network is particularly well suited for resource constraint and mobile devices, which cannot accommodate much larger networks. We have kept pooling operations to minimum and integrated skip connections into the network so as to preserve spatial information. Our network also employs a small number of kernels per convolutional layer. So we have illustrated the utility of the T-Net in retinal vessel segmentation, skin lesion segmentation, and interstitial polyp recognitions. Thanks. If you have any questions.